Everyone. Welcome to our Great Lakes section second webinar today. Today we have amongst us the presenter, Dr. Anderson, who will share his expertise in technical embroidery and its applications in composites and e-textiles. Over to you, Dr. Gashti, the moderator of the event today. Thank you.
Yeah, thank you, Ms. Akhtar. Let's wait. Probably we're going to have more people joining.
Okay.
Yeah, we're getting people.
Good morning. Good morning.
Good morning, Dr. Anderson. How are you?
I'm doing well today. How about you, man?
Yeah, thanks. Thanks for joining. I know it's a bit different time for you in Seattle, but
Works great for me. I'm in.
yeah, I know you're busy and probably you wake up early. So
I
you're
I've
perfect.
been on and off some mornings really early, some night. Today it's so cloudy and foggy out that so you know how it looks like how they do photography scenes with like the backlight that's like perfectly smooth light? Well, all of the light coming through is perfectly gray and there's no like direct beams anywhere. So I woke up today like, what is today? Did it snow or is it like morning or night? What is it?
Yeah.
Good
Yeah, I
morning.
understand. I've been in British Columbia before.
Yep.
I've been in this situation, like foggy and somehow, it takes several weeks you see sunshine. So
Yeah, that's exactly it. Yeah, it'll
I,
get
I
it'll get
like
more
to
soon. Hmm?
yeah, I like to get rain actually, just getting
Yeah,
rain, but
yeah,
after that just seeing the sun. But
yeah,
unfortunately it just stays foggy and just
yeah.
cloudy. It makes you like feeling lazy and not comfortable. But
Definitely does something to you. I noticed, actually, I guess it was last year we went down to San Diego in the middle of the winter. You know, it's beautiful weather down there, sun, and we were surfing and like bodysuits and everything else. And then I came back and I realized, man, you really do feel it. Like when you have sun on you and you're outside and you're doing stuff, like you really do feel pretty good. And then when you come back and it's just like rain and whatnot, you're like, I guess it's crunch time, it's work time.
yeah, yeah. Exactly, but yeah, let's wait for only 1 minute. We can wait for a few people to join.
Absolutely.
I don't want people missing, the introduction. But
Good morning, Mr. Anderson. I'm Tazeen. I'm also in Tennessee enjoying the sun with my family. It's a good
Nice.
weekend for us. And so
Uh-huh.
it's so cold in Chicago.
Oh, I'm sure. I'm sure. My partner's up in Albany, New York right now, and it's apparently snowing up there. So it's going to be a cold one for everyone out that side of the country.
Right.
Which city in Tennessee?
Gatlinburg.
Okay. Okay. I don't know that one well, but
Yeah, Smoky Mountains. We are looking for the bears if we can.
oh, nice. Nice.
My sons, we were here last year as well. They were like, we
Uh-huh.
haven't seen a bear yet. And I said, one day you will.
You will, and then maybe you don't.
Yeah, we don't want to witness that. We don't know how to deal with them.
I remember we were driving through Yellowstone and we saw a few get pretty close to the road too. And so we just kind of like you go nice and slow right by, you don't stop and you just keep going. And yeah, they're around. Big, big grizzlies too, not the small little black bears that we used to have out in Pennsylvania.
Right.
but not. I don't think it's. You can find them in that many in Tennessee. You need to go to Alaska or British
Alaska has a
Columbia.
lot. Yeah. Yeah. Tennessee has, I think, the little black bears, if I remember correctly, the little tiny shy, curious ones. I think,
Yes.
yeah, that's the one that they have down there a lot.
The view
Yeah.
from here is very cute. You can see the view.
Oh, it's beautiful. What a lovely view.
Yeah.
Oh,
Yeah.
it's gorgeous. You might see one.
Yes. From far. That's what I said to my boys.
That's right. From up high and down low from afar. That's perfect.
You're a ATCC member, right?
Yep.
Okay.
I've done a good bit of work over the years with AATCC, all the way from honestly from undergrad upwards. So it's a great thing. I mean, it seems too like, especially compared to some of the others, that has a really good active community in different locations, which is nice. And also they do a lot of good stuff for students, for scholarships for students, for projects for students. And that's been something also that's dear to me. So
And
that's
Dr.
nice.
Darcy has a students chapter in our section now opened up. So
Yeah,
we're excited about that.
that's excellent. That's excellent.
His
Yeah,
whole
for the
team is
first time
working.
happening in Kansas State, you know.
That's wonderful. That's wonderful.
Yeah, like we're not at the middle of nowhere. What people realize, we
Yeah,
opened this chapter, and a pretty good number of students we initiated, and I think
excellent.
I'm sure we're gonna grow more, get more students recruited, and I'm gonna put them, to anyway to let's say to do their job, to just be independent, but just supervising them from the back. But I
Yep,
think we probably have 20 people now attending. Probably we can start.
excellent.
Hello, everyone. Miss Akhtar, the president of the ATCC, actually, like ex section, shortly introduced. But I just wanted to again say to everyone, thank you for joining this today's ATCC webinar. Uh, for the Great Lakes section specifically, but we love to have other members from other sections. Today's webinar is about mass manufacturing smart textiles and composites with stitching, highlighting scalable approaches that integrate traditional textile processes with advanced smart and composite materials. And this topic is particularly relevant to ATCC members, and it demonstrates how established textile techniques are, such as stitching, and that how that can be adapted to other applications, especially on the composite factory manufacturing. I like to see that integration with like a medical textiles, especially because these are growing fields and definitely applicable. I would like to talk with you later about those, Dr. Anderson, because I'm doing some research on that, and I want to see if those technologies can be integrated on the, like orthopedic textiles. And it's my pleasure anyway to introduce Dr. Topher Anderson, holding PhD in textile engineering, graduated from Thomas Jefferson University. And Dr. Anderson is founder of Arachne Labs LLC, and his focus in developing mass manufacturing of smart textiles, and he teaches. So uh, we will have a time for questions following the presentation, but feel free to post them here in the chat box if you want. Dr. Anderson, it's with you now. You can now start the presentation.
Awesome, awesome. Let me go share screen. All right, send request for screen share sent. And there we go. And I'm going to do screen two and then share screen two. Awesome. Move this one over here and then actually pull this. All righty. So title of my presentation is Stitch Please, Not Your Grandma's Embroidery. So what we're going to look at in this is technical embroidery, technical stitching for different types of technical textiles. Just to kind of show you the larger meta point of this isn't just a hobby craft anymore, and some of these smart textiles and some of these stitching technologies now are being done in the thousands, hundreds of thousands, even the millions units per year. So we've started to grow from a smart textiles where it used to be more novelty, more fun, more playful hobby level smart textiles, and now we're starting to get into much more professional and scalable smart textile solutions. So what for this one, we're going to look mostly here at technical embroidery. So if you look back at historical embroidery, a lot of this is built on, quite frankly, similar principles with newer materials, newer types of motors, newer types of exchange, newer types of precision and accuracy. But if you look back here, I like to show this because this is an old punch card level embroidery machine. So this is the kind of one of those original computers, just like the original Jacquard was. But a lot of the techniques that we use for these are very similar, quite frankly, to what they used to be when the punch card machines came out. However, we use different materials. We're going to use different computer programs. We're going to integrate electronics. We're going to look at things like Cantonal for heating wires. We're going to look at things like carbon fiber for composites and other materials there that kind of open up the ball of what we can start to do with smart textiles and technical textiles. So as a quick piece, this is all based on textile.org. I've been putting more and more of my time into this. Textile.org is my training platform for students. So we're trying to keep this as an open training platform for people that want to come and learn about textiles. So there's been a lot of interest of students all around the world who might not have access to traditional textile programs, or for students who want to brush up on things. And so we're starting to add all of this into that textile. So all of these presentations, plus how we made the samples and other things, will all be on here for people to use and access. So we'll start off with this fun one. So this is for chenille embroidery, or K-head electrodes for ECG, EMG, and EEG. So if you look, traditional embroidery, chenille embroidery, has these types of fluffy-like structures where we can start to create loopy structures that allow us to start to work with the embroidery itself to create a high volume, very soft, fluffy piece that's integrated really into almost any textile. So we can start to put chenille embroidery into thick things like leather. We can do chenille embroidery into very fine knits that have a lot of stretch. We can do chenille embroidery into wovens, into plastics, into films. It allows us to kind of functionalize those in a new way. So what we discovered is that if we start to use these same chenille structures with new materials like silver-coated nylons or carbon fiber or carbon nanotubes, we can actually start to functionalize those individual surfaces and allow us to get data out of them. So it kind of is a 1, 2, 3 of materials, of functional yarns, and then also of electronics to process them at the end. And so this is one way that we're able to make these textile electrodes. These are fantastic for measuring heart rate. We can measure EMG, which is electromyograms. That's muscles. A muscle is a natural amplifier, so we can start to pick up which muscles or which sets of muscles are being active at any time. And then we can even do some research into EEG. Right now, that's a big popular one, using AI to process some of that data. So EEG has many, many, many lower quality, but a high quantity of signals coming in. And so because of that, we're getting thousands, if not tens of thousands of individual signals that need to be processed all at once. And AI is really good at doing that. And so we're starting to even see things where we can use textiles to do brainwaves and other types of reading as well. So we could do these again with silver-coated threads on the top here. Some of these are carbon nanotubes. We can do different things to functionalize those, to color those. And this is kind of, to me, the opening salvo of how do we start to use embroidery to create structures that are unique with unique materials that can integrate directly with electronics. And so some of these are structural based, like that volume that we see on these, that nice puffy region, that allows you to have higher conductivity because essentially you have resistors in parallel, and that gives us a really nice area for a conductive surface to get data out of. So this is kind of one of the early ones that I look at to kind of show the case of how we can start to functionalize a more traditional textile using technical embroidery. One of the other pieces that's interesting about this is materials usage. So we're not using materials in a way that we're either wasteful with them. We're really only putting the threads exactly where we need them and using only the amount that we need. And I think that's a common piece specific to stitching, which is the one I focus mostly on. So we're going to switch gears here into a totally different side. So this is W head embroidery, or I call wire embroidery, is the easiest to remember. So for wire embroidery, we have three sub techniques. We have tailored wire placement, TWP, tailored tube placement, TTP, and tailored fiber placement, TFP. And so each one of these has a slightly different technique that we use, but they're all ways that we can put materials into existing fabrics, into existing sheets, into nonwovens, wovens, knits. It doesn't really matter from a substrate perspective. So here you'll see this is kind of the basic premise. We have a frame that moves in the X direction. We have a frame that moves in the Y direction. We have our base fabric, which doesn't actually have to be a fabric. There's a lot of different materials inside of there that are pseudo fabrics that would also work. And then we're using a needle to couch stitch or zigzag stitch over top of a functional yarn or whatever the wire or carbon fiber or material is that we're trying to connect. Now, this process is very materials agnostic. I can stitch down 16 micron carbon nanotube on the fine side, all the way up to about a ½ inch to 3/4 of an inch garden hose on the thick side. So we're pretty agnostic into sizing there. Generally, stiffness is something that I look at more. If you're going to stitch a wire down that's thick like a coat hanger that doesn't bend very well, we can still do it, but we have different techniques than this technique. And so there's different ways that we can apply things. But as long as that wire is a bit ductile or a little bit flexible, we have a lot of options on how we can put it down. So with this, you'll see at the bottom here, we've put a fine wire down. This is a basic off-the-shelf wire, nothing very fancy or special with this. Just to start to show you, we can start to route patterns or wires throughout a textile quite easily, actually. So this is a fun little one just to kind of show what some of the possibilities are. So this is a production set of these small little dollhouse heaters. So what we did for this one is 3D printed a dollhouse, very simple, I think 250 by 250 millimeters. And then we started to look at how do we wrap a heater such that it fits around all of the pieces. Now, this doesn't have to be small. We can scale this up with the click of a button, and then you can go to a full room-sized heater or something much larger than that. And it's very easy from this perspective. But the true test of this one was looking at the automation in the programming. So for this one, we just have to get the outline of where we want things, and then our software will go through and start to route the pattern accordingly so that we get even heating. And so this one starts to look at, again, these radiant floor heaters. This could be also for roof heating to get snow off roofs. This could also be for concrete or driveway heating. This could be for specific other heating applications. So from my end, I get a lot of heater questions. Heating is one of the ones that I think is the most easy to grasp and representative of this technology. And a lot of people will ask me in some of these things, smart textiles is really cool. We like it, but it seems like it's been coming for 20 years. Why isn't it here yet? And I'll counter that by saying, well, I think car seat heaters and some of these wire heaters for car seats is exactly what you're looking for. They're made in the hundreds of thousands of units up to the millions of units. They're used, they have an actuator, which is a heating element, a temperature sensor, and sometimes even a pressure sensor. They're integrated directly into a variety of different textile substrates, sometimes nonwovens, sometimes more luxurious outer fabrics. And they allow us to start to have that smart textiles interaction. It's just not a human wearable like a sweater or something else. And so with that as kind of a premise, I think this is another opening salvo to manufacturing in these, because these machines and the factories that make these can make many, many, many thousands per day at an extremely low cost. And that's all, again, driven by the automotive industry. So this is a very important one, I think, to get into that heating space and how we start to scale some of these technologies out. Here's another fun one. These are composite silicon heaters. So this is starting to fuse the gap between some of the other heatings and composites curing. So these are variable density heaters. So what this means, I use these actually for teaching, especially with younger students. We can put an ice cube on each one of these and see how long it takes the ice cube to melt. And then we can do a back calculation for how much heat is in each one of these little square regions. What is the wattage of each square, just based on how much wire is there. And then we can start to teach some really interesting thermal things and thermal engineering for textiles. And so this is a fun one that we've done a couple of times. It's all fiberglass that I put down with the embroidery machine, and then I put the wire down. This is a basic copper wire, enamel coated, nothing fancy on it. And that's enough to give us a really nice heating profile. You can see over here, we're starting to get different heating profiles on there. We can also do some other fun heaters. So different filled heaters, edge heaters. We can do wraparound or stretchable heaters. We can do heaters that fit any size or shape. My lab at Arachne, we make custom versions of heaters all the time for people on different fabrics and substrates. We have different production equipment, and then if you want to do this in production, we can connect you to companies that have good equipment and good reputation to be able to make this. So these kind of heaters are pretty well used and pretty ubiquitous throughout different types of smart textiles. Now, from these, material is something also that we kind of touched on. So we have lots of options of materials for heaters. We can do fine wires, we can do Cantonal, we can do copper, we can do substrates. So both of these have stitched fiberglass substrates underneath, and that helps to protect the heater. We can do heaters that are very, very light and embedded deeply into a structure. The material is, again, pretty agnostic. If I have my druthers, I generally tend to go towards more common material heaters. So that's things like traditional fabrics, traditional materials, plastic threads, polyester stitches, very nice in this regard for holding materials down. There's some organic fibers too that I like. A lot of organic fibers, especially for the base mesh, if we're looking at that side of it. But from a material standpoint, we're very open towards what you want to try, whether that is a thick wire, a thin wire, some type of 3D printer filament, or other materials in this space. So to step back from the materials, we keep getting a little weirder on the materials, a little weirder. This is a fun one. So this is EL wire. So this is actually a wire, electroluminescent wire that we can start to do things with. Looks like a neon sign. We've had some fantastic customers through the lab from Hollywood, from costuming, from New York Fashion Week, all looking at how do we start to get that new visual aesthetic that we're looking for. And can we start to put some stranger materials or lighting directly into the fabric, into the thread, or into the stitching itself? And so these are fun. I find these quite fun to make, and they show really well. I haven't had as much interest in this space just because, again, they're a little more on the novelty side. But the idea with these is, what if you have something like a pizza shop or something and you want to have a neon sign? Well, if I ship a neon sign that could break, they go out. Well, what if I roll it up and I can just ship a low-cost rolled flexible sign? You hang it up and you're good to go. That's another option inside of this. But for this one, again, we're using stitching and combinations of stitching, traditional stitching to create some design elements. We're using multiple passes of different types of EL wire. This is very common EL wire. We can actually get much finer, and they now even have EL thread out. So we can really get tight details if we're looking to get that. But this just allows us another visual aesthetic because, again, sometimes it's not just technical, sometimes it's visual too, especially if it's consumer facing. So this is another different one, looking at a different way of routing. So this is a pair of pants with different sensors. Each one of these actually is a muscle sensor at the bottom. And then these two are, this is our output so that we can start to talk wirelessly. And then these two are also swipe sensors so that the user can actually interact with the garment, turn it on and off when they need. But this is how it kind of comes out on a flat head machine. So these machines, this allows us to do different types of wire stitching as well as the flat pattern on the outside. We can do different touch buttons in there. We can align for different wires or types of wires. And then something else that's particularly interesting is how we can do pathing in the textile. So in this case, we're using a very highly elastic spandex-esque knit, and we want to make sure that we still maintain some of that stretch inside the final piece. So we can do that by serpentining or curving paths throughout the piece. We can start to add areas that we have more stretch, or also put threads down to start to support the structure of that piece, allowing us areas that don't stretch. So if we have technology around something, or if we're trying to look at maybe reinforcing it, those are areas that we might put a little ground layer stitching down to help ensure that the stretch happens around that piece, but not inside of it. These are all different methods that we have for constructing. And so this is a fun one. I've explored this at a couple different places in the past. A lot of interest in trying to make these multi-sensor systems that output to a common node, and that also simplifies from the electrical engineering side. We can start to simplify this individual, we call it the puck, to just collect the data and then spit it off by Wi-Fi to something else that does the processing. And that way we can start to really work within the space of the textile is just sensors and getting the data to this Wi-Fi. And then the Wi-Fi is the bridge between this and the greater system that's doing analysis on this. And that way we can use more traditional computers and large servers and other things that you're not going to carry on your back to do the processing. And that's a really nice recipe there for being able to get data out of a textile and process it in real time. So I'm going to switch modes right here entirely. We're going to go into the composites mode. And so composites is another one of those that I find really exciting right now, especially in the US right now. There's an enormous amount of interest as we're making more and more of these ultra lightweight, ultra strong structures within the US. And so composites or thermoplastic or thermoset composite parts essentially use a carbon fiber or another composite fiber towing, and we start to be able to do some types of zigzag stitch to put this fiber down into what we call a preform. And so this is particularly interesting. So if I step back in making traditional composites, I'm usually taking woven laminates and I'm stacking up the woven laminates and I'm cutting a layer out and I'm stacking it and I'm cutting a layer and I'm stacking it and I'm turning it and I'm cutting. But what happens through this is one, there's a lot of cutting steps, and that means there's also a lot of waste steps. So everywhere around the outline is waste. And so that's getting thrown away. And carbon fiber is extremely expensive material. It's gotten a lot cheaper in the past 10 years, but it's still a very significant price driver to composite parts. And so the thought of stitching these is if I can start to take the carbon fiber and I can start to stitch it down, I can actually put it in the exact directions of the principal stiffness of the part that I'm trying to make. And this allows us to open up an entirely new aspect of making composite parts where we're not only saving material, we're not only using the material exactly where we need, but we're also putting the material in a structure that we need. And that structure allows us to do things like have higher areas of bendability or flexibility or high areas of stiffness in the part. And so by tuning that, we can actually create a bike seat that when you make it, it bends nicely over the wings and is very stiff down the center. And this is a combination of where the fibers are, how many layers, what the order and the direction of the fibers are in that layer. Do the fibers comply with the direction of principal stiffness of that part? And if so, can we start to use that to build up a substructure inside of there to create these, again, extremely lightweight, extremely material sensitive, but strong parts? And so carbon fiber is one of the more favorites of this technique, just because we really get to extract the last bits of stiffness out of it. So this here on the left-hand side we call as a preform. What happens, this one in particular is a thermoset. And then this one is actually a thermoplastic, and these are thermoplastics below. So thermoset just means we're going to cut this out afterwards and inject epoxy into it to make it a solid part. And that epoxy injection is what transforms it from a textile to that composite part. So that's where the fusion bridge is there. And then for the thermoplastic parts, we're going to take a piece that looks very similar to this out, although it's going to be stitched on plastic and not fiberglass mesh or another mesh. And then we put this into a hot press and press it. And that's, again, where we take this textile preform and we turn the textile preform into the composite part that comes out. So down below we have natural fibers, which is another big one, hemp fibers and flax fibers. These are all doable in this composite preforms as well. And that opens, again, doors up for different materials testing. I've had a lot of interest from the hemp fibers in the US of trying to do different new materials. And maybe some of the stalks or whatnot, maybe some of the fibers that are coming out are not quite as fine we actually have a benefit from that in composites. If we can leave them a little more natural, that gives us a little bit more strength in general that we can start to use and create these, again, composite parts that can degrade over time, which is another exciting one. We can use bioplastics and other types of plastics, chitosan composites, to set them. And that allows us to make these very exciting natural fiber composite parts. So here we have a couple other things. These are shoe blades. So this is when I say a preform, a thermoplastic preform, what I'm talking about. This is exactly how it comes off the machine. You can actually see the different fiber angles here going across and then some going long. So in general, when a composite's made, the long distance of the fiber goes against the bending. So you have a very high stiffness here. And then we have lots of bending capability here. So this is the part that comes out after we hot press it. What this part does is we have a high region of bendability here. So this acts spring-like, and then this is very stiff down here. And so this allows us to create these extremely complex and very strong parts that have different tailored properties. High bendability in some regions, high stiffness in others, and that all comes from how we construct the textile itself. Cooling tubes and tube placement. This one I also think is extremely exciting. I'm surprised that we haven't had more interest or more projects in this over the years. Um, but tubes allow us to start to pump different fluids through a textile or air through a textile. Or we can start to do things where we leak water through a textile. This opens up an enormous amount of very creative and interesting doors in thermal textiles, as well as sensing. Because if I'm pumping air through the textile and it has an ability to leak out at different points, well, now I have a sensor in the textile that doesn't have wire in it. And that's kind of a unique proposition inside of places because there's areas like MRIs or whatnot where we can't have wire, but we can gladly have a sensor inside of there, especially if it's like an air-based tube sensor. So this opens some really creative doors here that we can start to use and make tubes inside of textiles. And again, our tubes, we can do fine tubes, thick tubes. As long as the tube is somewhat ductile and flexible, we can start to stitch that down and add that in as a piece. Next, we're going to start to get to flexible circuit construction, and this is another fun one. This is some of the stuff I used to do at Microsoft out here in Seattle when I worked there. We look at different ways of making touch sensors or swipe sensors or integrating of circuit boards. So this opens a whole nother set of technologies where one of the big things is how do we create a rigid to soft connector? How do we start to bridge the gap between these rigid circuits that we already make in bulk and also these new flexible circuits which are worn? And stitching is a phenomenal way of doing that. We can actually have the stitching machine automatically locate where these boards are, look at them under a camera, align them, do stitching, put the conductive threads directly through the stitch holes, and then to be able to create the sensors themselves out of that. And this one over here on the left-hand side, this is a touch sensor where we can touch each of these touch points and that brings it into the board. We can do things like vias in traditional circuit boards. A via essentially is a small hole from the top of the board to the bottom of the board where we can send a signal through the board. And that allows us to send signals over top or underneath each other. We could do the same thing in a textile using plastic thread to kind of create these bridge gaps and then to be able to create a conductive thread over top of them. We also have the ability to stitch in different holes. We have large holes that we can stitch through. We can have fine holes. So this is off-the-shelf Adafruit board. Again, this is a 0.1 pitch board. There's nothing special or fancy about this in the regards that it wasn't set for stitching. And we can stitch directly into those and create these nice stitch holes too. So we have a lot of options here for doing touch sensors or board integration, routing wires, sweat sensors, temperature sensors, you name it. This is a way that we can start to integrate those from rigid to flex. Another one that we have here is we have the ability to take sequins. And so sequins are little traditional plastic pieces. Again, we see these a lot inside of, I don't know, ballerina dresses or a New Year's suit or something like that. But to me, a sequin is a single-sided flex circuit board. And this allows us to mount electrical components on there. And once you start to mount a component on there, a lot of electrical components come in set form factors. So 0603 is a standard. It means 6 millimeters, 3 millimeters. we have a lot of different capability there to be able to do mounting for these. And so we can start to fill in all of these components and start to put very specialized electronics in and automatically connect them to the embroidery or to the fabric or to the substrate. And this technique allows us to do big things like grids of sensors, touch sensors, grids of temperature, grids of lights, or grids of oxygen sensors. We can start to cover an entire circuit like a blanket with sensors to be able to do things and interact with that. And because it's fully automated on these sequin devices, we can go very fast and we can start to stitch thousands of these, if not tens of thousands of these down a minute. And so now you're starting to get in a production case to the same level of placement that becomes needed to be able to make these cost effectively and get these out. At the end of the day, all of this technology that we're looking at here has to be made cost effectively, has to be beautiful, has to be functional, and has to hold up over time. And so we're getting to the point now where those are all converging, and we're starting to see really interesting smart textiles come out in scale. So I think this one still has a lot of fruit to go, and I think this is going to be one that appears much more in the near future. Touch sensors and textile keyboards. So the idea of this one is how do we start to take some of these more traditional textiles or traditional wearables and that are rigid and start to turn them into flex boards. So this is a board we designed here. It has Wi-Fi or Bluetooth, different levels of touch sensors on top of there. I think 24 touch sensors for this particular board. And this allows us to start to do things and interact with that textile to create things like keyboards and then to wirelessly or Bluetooth send this away. So I have one of these sometimes I use for presentations. I'm not using it right now. I'm using my mouse. But this is a really neat and interesting way of starting to interact because this is a technical layer that could be placed inside of any non-technical layer. So if you have a suit, this could be the liner in the suit. Or if you have a sweater, this could be a band that goes underneath of the sweater. And we can actually interact with materials above that. So this particular sensor is designed that it can interact with up to 1 inch of glass on the other side of it. So essentially, that's going to see through any textile or leather or set of textiles or polyester filling on top of a core shell or something. It's not a problem. We can start to read through that. This is how we start to go from these rigid wearable solutions to these soft wearable solutions, and then start to do it in scale again. So another one that I get questions on is commercialization. How fast can we go? This looks like it's going to take forever and be really expensive, and the technology is not ripe there. I've heard a lot of these. I'd just like to pull this one out. This is bend-shaped mask. So bend-shaped mask is kind of my ideal one for how fast we can move with a project. So this is a mask, a stitch mask that was done during COVID. It has some very fancy features. You can look it up afterwards. But the thing that I want to highlight on this is the speed that it was. We went from 1 prototype to 20 test prototypes in the first week. 168 variation styles, different materials were tested in the following 2 weeks. So at week 3, we were done with that. Manufacturing optimization so that we could start to scale up and ramp was in week 6. Then we started going from 200 prototypes to 2,000 prototypes in week 7. And then we immediately turned on one of our factory friends that we knew. And because the files were done and set, and we knew how to scale them, we knew how to get everything done. We knew what was coming because we'd already done the small batch manufacturing in-house. We were able to go to 800,000 units per month by week 11. And then the company was sent off to a hedge fund in week 42. So this was our commercialization and how fast we can move. Because again, a lot of the work is done up front. You can kind of see the schedule is compressed here. Up until week 6, it does look like we are really running. Usually it's a lot faster even for prototyping. However, we knew that we were going to some very special production machines after this, so we had a little bit more work to do, and then we gained it right back on that week 11. So this is a way that we can start to scale out and go quickly with these. So without further ado, I'll leave this up to you guys on questions or things that you want to see or hear or whatnot. I just again want to say if you guys have any interest in helping build educational platform that's open for students, let me know on that. All of the presentation here, as well as directions to how to make these different materials or whatnot, are inside of these courses. We have courses on embroidery. We have courses on fabrics and fibers. And again, we're starting to build a team just to start to help out with textile education in the US because I see some big gaps there. But I hope that was interesting. And yeah, let me know what you want to chat about.
Thank you so much, Dr. Anderson. That was fascinating. You summarized everything here, the potentials for this specific application, and it's growing area to me. They're going to be demanding in the future, and I think this can be even integrated in other applications. Even thinking of using this technology for agriculture, developing sensors that could be used in agriculture areas, even for climate. You want to have some sensors that could be. Imagine you have a flag hanging somewhere, and it has some sensors that you can put some sensors inside. You would be able to monitor the climate, temperature, outside temperature, rain or moisture. All of these can be integrated, and especially on these, the light, like a neon based sensors. I was thinking of because I have some connections in Canada. They're producing, like let's say, visible vests for laborers. So
Yep,
imagine those people are working outside for on roads. They can use this instead of fluorescent or some other, like components they're using. This can be something you can turn it on or off whenever you like. So, and there are lots of areas we can think of integration of this technology.
they're coming. I mean, actually, the agriculture one is particularly interesting. So, the initial tube tests that I had done in different tubes were for agricultural. How do we start to pull water and do like drip water feeders over large areas? And that was one that kind of came up as an interesting, like agricultural technical textile. And I've seen more and more of them come up now that I'm a little bit more aware in that space. But yeah, I think that's a fantastic play.
Yeah, I recently got award from Kansas Agriculture Department to develop non-wovens out of hemp for
Yep,
agriculture purposes
yep.
to control moisture inside the water. And I'm thinking we can work probably together on integrating some of these sensor technologies in what I'm gonna develop in the lab.
Absolutely. And there's different equipment too. Like I have a bunch of equipment coming, brand new, that allows us to do things like giant rolls of fabric. So we can take I don't know, couple thousand yard piece of, I don't know, non-woven or whatnot, and start to stitch, whether it's wires or tubes or whatnot, down or across it and make patterns inside of there. And so that's particularly interesting if we're trying to do those larger pieces. In the past, we've had some interest in fiber optics, actually. So with fiber optics, we can actually start to detect if people are walking over fields or walking over areas, and that can allow us some other interesting data points inside of there of, I know, are there deer coming by? Are there other animals in the area? Have we tilled the field properly? So some plays inside of that as well.
Mhm. Yeah. So, attendees, if you have any questions, feel free to ask Dr. Anderson.
I really like that part of textile keyboard with Wi-Fi and Bluetooth. I'm sure it
Okay.
will be very interesting for the student members of our section.
Sure, sure. I think I might even have a few extra if you want me to send you one.
Sure, we'll be happy to have one. And definitely thank you so much for taking out the time from your busy schedule and accept our invite for this webinar and also giving us the opportunity for the students to ask any questions and that platform that we have set up for the students for extra knowledge. We definitely need those. In the future, we'll be contacting you if you have any other questions or any other, meetup we can arrange for the students.
That'd
So
be wonderful.
yes,
That'd be
allow
wonderful.
definitely. And thank you, members, for joining today. It was very helpful and informative webinar.
I
And
think my student Arif has a question.
Excellent.
Hello, this is Ariful. How are you?
Hello, RF. Hello, RF.
Uh, my question is like the main problem is like during our day-to-day lives, we face harsh condition like raining or extreme heat. So, did you do any test on the durability of these products and also like washing and how long this functional yarn can be uh, do the normal work that can do like can you share some and also like I think the smart textile is mostly needed for people with disability. It's like if let's say someone who is in wheelchair,
Hmm.
if his uh, bottom part of his cloth can be made with piezoelectric yarn, which can generate electricity and perform other works. Have you done this kind of works?
Hmm. So let me break it down into three kind of subsections. Section one is environment and washability of smart textiles. Section two is essentially use cases within both disability and then other spaces. And then section three is energy harvesting in textiles. So I'll start with actually the easiest one, which is the last one, which is energy harvesting. So unfortunately, as much as I love the idea, I have yet to see any energy harvesting that starts to really add up in the wattage that we need to actually run any chips or significant pieces. And so from energy harvesting in textiles, while I would love that, and I think that's kind of the holy grail because then we don't have to carry batteries around. Usually, right now, most of the papers that I've seen in that space are in the nanowatts of power generated, which there isn't really a great chip that we could run with that. Sometimes you can get some signal out or some sensor. Um, it's something that is actively being researched, but again, in my like research literature search, and I try to keep up on it, I haven't seen anything that generates the even like the level of wattage that would be required to start to run smart textiles that do useful things. With that said, there are some converging pieces on that. So, Microchip, I believe, has a line now of nanowatt electronics, which are extremely exciting because it's significantly less wattage than we were using previously. And from a year-to-year perspective, the wattage required for computation is going down. Um, there are some interesting spots, it looks like, in there on high surface area electrospun nanofibers. So there's some stuff there, but I have yet to see a convincing paper in smart textiles on power generation. I think we're probably, on my guess, unless there's some great breakthrough, probably 15, 20 years away from that converging with electronics. So to step to the next one on environmental, so water is actually one I much prefer. Water is cool. So we can work with water, we can work against water. There are coatings like Parylene D coatings where we can surface coat it, and then the surface is super hydrophobic. We can actually design the electronics in such a way that we can do more traditional conformal coats on the outside. We could do things like coating it with plastic. And sometimes the question I have is, do we really want to fight the water or do we just accept it? And so there's different rules for those. So if I'm doing a high power system or high current system, I have to fight it. Because if I'm making a heater, I can't have water in a heater. That's dangerous. But if I'm doing something like a very low power capacitive touch sensor, like I look at it and I say, does a little bit of dampness in the sensor actually matter? And usually no, and sometimes it even makes a sensor better. And so if we start to look at the structure of the textile around it and look at it holistically, sometimes water is actually a really good thing if we want to start to build higher conductive regions, or if we're trying to be able to place out things, place out areas that have high hydrophobicity. Alternatively, the coating solution works. So from a lot of these, we've done different wash cycle tests, up to 50 wash cycles with especially capacitive touch and circuit boards. That's not a problem. We get through those fine. We do lose some conductivity on some of the conductive threads. But again, if you're using things like carbon nanotubes, we don't lose any conductivity there. They stay the same because it's through and through carbon nanotube. So if somebody came to me and said, yeah, I need this to be able to do 10,000 laundry cycles, I need it to be able to stand up to phosphorus and all this other stuff. Well, we could do that. You're just going to use a more expensive material for that. Whereas the other side of it is sometimes they're single use. So that brings us to the last piece, which is like for different hospital cases, disability, things like that. So sometimes the use case of the textile or smart textile differentiates what we can do with it. So for instance, in hospitals, almost all of that has to be incinerated afterwards. And so to be able to use a smart textile there can be a very clever solution just because we don't have a lot of the environmental controls because it's going to be used once or twice or three times. Not that I like that from a sustainability aspect, but that's just how we've set up hospitals in the US. And so from that perspective, there opens a lot of doors in, yeah, disability, I think is a very good one to investigate. I think hospitals is a good one to investigate. But I think it's bigger than that because, again, if you're looking at wearable, sometimes the most exciting smart textiles are not the more traditional wearables that we think of. So, like a cover for a wheelchair seat could be something, a pressure sensor in there. We could have the interior of a car or having sensors throughout the headliner of a car so that we can touch and do things in that perspective. All of those to me are still those smart textiles. They're not necessarily wearables, but still serve the same purpose as a wearable. And sometimes having them track with the object that needs is actually easier than trying to track the human itself. So anyway, those are where I kind of think there. But overall, yeah, there's a lot of research into use cases of where we can put these things.
Thank you.
Thank you. So we have another question from Dr. Dawood Hussein.
Thank you very much for giving me this chance to ask the question. So, Dr. Anderson, it was quite an informative presentation. It's really good to see that how you have used the technical textile products, I mean, e-textiles and non-e-textiles product. Thank you, Tazeen, for inviting me and my student chapter members to be part of it and learn the valuable insights going on in the world. So my question is basically, I've got loads of questions, but I'll ask just one basic question. It's about the embroidery technology. Is it the conventional embroidery machine you're using? Because I've not seen any machine or equipment image in your slide. So can you tell more about it? I mean, is it this kind of technology is commercially available, or is this is
Right.
something which you have built in-house?
Yep. So so what I have right now is I've made an order to an equipment manufacturer, actually multiple equipment manufacturers that are putting some machines together that are custom to what I need to do. And so that allows me to actually do a lot of these. So I have a couple shipping containers of those coming in, and we're sending those out to different schools actually as part of textile.org to try to get more equipment and capability. So some of these are more in the traditional space, and then some of them are modifications of the equipment. So there are things that we have like 3D printing on an embroidery machine, which I don't even think I have slides of that in here. That's something that we do in-house. Different soldering on the embroidery machine, ultrasonic welding on the embroidery machine. All of those are unique to our setup at textile.org and unique to the equipment that we've pulled in from different manufacturers. And so from an equipment standpoint, if you're looking at making these or setting up a lab or whatnot, keep in touch because, again, I have a lot of it coming in that's been custom made so that we can make these types of materials on them. And there's going to be more and more of that coming because I see that as a piece that here in the US, we need to do more.
All right.
Yep.
So thank you very much. I myself have been working in this. Sorry.
Continue. Sorry.
Um, no, this is fine. Thank you very much for your detailed answer. I myself is also a researcher in this e-textile area. Primarily, we have worked in the developing the sensors by the knitting technology. So we've got a
Mhm.
flat bed knitting machine, so in which we have developed like ECG, respiration, and temperature sensor, and more recently EEG sensors also. But again, there are some limitations, in the knitting machine as well. And so it would be really interesting, like the way you are, building a customized embroidery technology as per the requirement of the application area. So I'll be in touch with you, of course, in that context, that if we can, produce something like this or the basic version at least, so
Yep.
that we can produce some samples and compare that with the knitted samples also. But because
Absolutely.
this is something, um, and I would be also interested if you have got some research articles. I would also like to see because probably you have mentioned the things in more detail in it.
Yep. Yep. So I have a couple articles I can gladly send you. My what we do with my lab is we try to make something and post it out there. So we post it to the textile.org website, or we'll post it to LinkedIn, or we post it like as soon as we make something, it goes right out for feedback. And then we'll work with people and do testing and other stuff after that. And there are some papers out there that we've done as well. My side focused is on that manufacturing because I think that's the piece that is, to me, from a research standpoint, the most interesting. And also it's the piece that holds us up, I think, as a field. Because I could say, I mean, at when we're at Microsoft, we're making these really cool samples, we're making hand prototypes and whatnot. But at the end of the day, if you can't scale that and you can't scale it cost effectively and reliably so it can go through testing and it's the same every time, usually those projects go out to die as prototypes. And so I really like to see the things that go through the whole pathway from here's a concept to here's how we make the first 10, here's how we make the first 1,000, and then here's how we make a business model and start getting those out. And I think to me, that's exciting. And so from that, yeah, custom equipment is required for that because if you're running a stitching machine super slow to stitch it down, and it goes like that's not an idea because if it takes 4 hours to make a single part, you're never going to sell that at a good price. You need to be able to make these at many thousands per hour at a very reasonable piece. And so I think from my end, manufacturing is a very important part, and the equipment that we use is very important. Like, so knitting is a fantastic technology, and knitting has a lot of advantages over stitching from speed, from the ability that we can start to make these very large materials, are also true to shape materials, which is a whole nother side of this. So I think these technologies start to complement each other. I wouldn't say that I'm an embroidery only person or stitching only person. I see from the way that I work with smart textiles, that's my finishing step, but I still need a textile to stitch on, and I still need some other material or something that's created. So I'd love to work with you guys. Yeah, reach out and we can chat more. I'll send you some more details, and I can even show you some of the new equipment. I think it's coming in actually in about 2 weeks, 3 weeks. So we'll have a whole lot of new stuff coming in to be able to look at.
Thank you, Dr. Anderson. Yes, definitely. I'll contact you. I'll be in touch for the future collaboration. Thank you.
Wonderful. I look forward to it.
Thank you, Dr. Hussain. We have in chat box, we have a question. Do you have a reference document for where we can purchase some of these threads?
Sure.
Uh,
Sure. Shoot me an email and I'll give you, I have a whole list up, and then there's also a list on textile.org for materials. I'll step back for one piece. I get a question also like, which is the best conductive thread? And my answer to that is like everything in textiles, it depends. So we have threads that are highly conductive, but maybe they don't launder as well. We have threads that are more resistive, great for building pressure sensors. We have threads that are mixed material, copper core threads. We have threads that are twisted wire threads where actually we're using a covering process on it. So we have extreme conductivity, but they're quite weak. Um, so what I would ask there inside of that is, what is the end goal of the piece you're trying to do? What is the end technology in electrical, or if there's something non-electrical too, because there's some interesting properties of conductive or silverized threads that are non-electrical. But what is your overarching goal? And then we down select from that. Because again, there really isn't a one size fits all thread for this at all. And it also depends on what you're trying to do with it. So if you're trying to do knitting, there's a very different size thread than I would use for stitching. And if you're trying to do stitching, well, if you're doing the chenille fluffy structures, it's a very different thread than if I'm doing straight stitching with a bobbin or a rotary hook. And then sometimes even if you want to get more complex, in stitching, we have top thread and bottom thread. So we have our needle hook and our hook working together. Well, the threads that we can put in each one of these also can be different. So we can have conductive top, conductive bottom, non-conductive top, non-bottom, and mixes matches either way. And so those all kind of interact. So shoot me your details and I'll try to down select and tell you which ones I see as probably the best for your application. There's a lot of good ones out there, and there's also a lot of bad ones. I'll tell you that. We've tested, I think at this point, probably about 700, 800 different conductive threads the past 10 years. And I would say about half of them are really not good threads that'll just be frustrating to work with. And then half of them start to have different variations as companies start to figure out what their secret sauce is. And some of those in that top like 10% are really nice threads, especially now. The research is still continuing every month on thread development. So if you're interested in that whole side of conductive threads or making conductive threads, let me know because I know a couple contacts that I can gladly introduce you to that will start to do that conductive thread manufacturing and customization and teaching for you.
Thank you so much, Dr. Anderson. Yeah. Is there more questions? And also, I recommend to connect with Dr. Anderson through because I know that you are very busy in LinkedIn.
Yep.
You're
LinkedIn works great. Hey, I'll pull it up real fast. You guys can see it. And that way you can grab the thing, share screen. This way, if anybody wants to reach out on LinkedIn, that's an easy way to get in touch with me. I post all of the new samples that I make. I post to LinkedIn. I post to textile.org. This is one of the ways you can see all the new stuff that we do down here. I post it up, whether it's production batches or new tests or samples or things that we discovered. So feel free to reach out to me and connect. And yeah, if you have questions or whatnot, I can easily forward you over to my other LinkedIn connection that knows how to do it. So if I don't, somebody else will, and we'll just kind of get you along the right path there.
much. So, more questions? Um, I think we should close now this presentation. But again, thank you so much, Dr. Anderson. Feel free to share your question with Dr. Anderson, and we would love to. Actually, it's somehow one of the reasons we are promoting these webinars is promoting, let's say, networking and trying to help different businesses, different ideas, sharing knowledges. And what I think I encourage the Great Lakes sections and even students to be part of these webinars, participate in these webinars, what you have actually as a research to present. Feel free to shoot your email to me, Dr. Our team, and also Miss Akhtar is available as a president. She can answer any question you may have. But again, thank you so much. Thank you so much,
I
everyone.
appreciate it. I appreciate you having me. And again, yeah, it's textiles in the U.S. is a small community, so we gotta have to stick together and work together at this, and that's very important to me. So again, if you ever have anything now or in the future, please reach out and we'll chat. I'd love it. Thank you again, guys. Appreciate it.
Thank you so much. Thank you,
Thank you,
everyone.
everyone, for
Have
joining.
a wonderful day.
Yeah, you too.
Thank you very much.